Hello and welcome to this lecture on analytic function. In this video, we are going to see one more property, very important property of analytic function. So the statement will be prove that real and imaginary parts of an analytic functions are harmonic. Harmonic represents if I am taking that f of z as u plus iv. Okay, so here the real part will be u of x comma y and imaginary part will be u of function of u of x comma y. So it has to satisfy that uxx plus uyy equal to 0, and here this has to satisfy vxx plus vyy equal to 0. So for this, let me take that f of z is equal to analytic function where in the form of u or u plus iv, where u will be the function of x comma y, as same v is also a function of x comma y. Then we have to show that it has to satisfy a Laplace equation. So a Laplace equation means uxx plus uyy equal to 0, as same for v. Now we consider the given function is analytic. Analytic represents it will satisfy the CR equations. It will be of ux equal to vy. So that's it. Here they have written in the form, general form. Vx will be equal to minus uy. So then I may differentiate the first equation. I may take the first equation and I may differentiate it. So we know that ux equal to vy. So if I differentiate this again with respect to x, uxx will be equal to vyx. Okay, the same thing. Next, we will differentiate the equation 2. Equation 2 will be uy equal to minus vx. So here it will be uy y equal to minus vx y. Okay, while differentiating with this, I am getting the next value. Here it will be minus, and I am adding up both 3 and 4. It will be in the form of dou square v by dou x dou y minus dou square v by dou x dou y. So simply what it mean, here it is uxx plus uyy. See, both are same. If I differentiate v twice with respect to x and y, differentiate v with respect to y and x, both are same. So definitely it will be equal to 0. So it will be equal to 0. This will be equal to, this term will be equal to this. Therefore, this term becomes 0. Okay. So now we prove that u is satisfying a Laplace equation. Therefore, u is harmonic. Next we go for y. So let me take that first equation, that will be ux equal to vy. So if I differentiate this equation, you will get uxx here with respect to y. Yeah. So uxy equal to vyy. Okay. On the next, I am taking the second equation, that will be uy equal to minus vx. If I differentiate with respect to x, it will be u xy equal to minus vxx. Okay, so same, that will be a sixth equation. If I add both, here it will be uxx plus vxx plus vyy. So and then if I add both equations 5 and 6, I will get this term. See, dou square u. Here it is xy, here it is yx. If I differentiate any of function with first variable and then second variable, or else if I differentiate with y and I go for x, that both are same. This term will be equal to 0. This term is already equal to this. Therefore, here it is equal to 0 now. Then this will be equal to 0. Therefore, it satisfies the Laplace equation. Then we say it is harmonic. So finally, we prove that f of z, u and v are satisfying the Laplace equation. Therefore, u and v are harmonic functions.